see synchronization in complete graph. We will see two algorithms that are the Christian algorithm and the Berkley algorithm, and then we will discuss a bit about the structure of the network time protocol. Both algorithms, the Christian and the Berkley one, assume a centralized time service that try to provide time and synchronize the others. The Christian algorithm is an external synchronization algorithm and uses a time server S that receives the signal of time from a source that can be UTC. And the Christian algorithm works probabilistically also in a synchronous system, as long as the asynchronous system is synchronous enough for you, and the synchronization that you can reach with the server depends essentially on the possible variation of that round trip times have during the execution of the algorithm. The algorithm is really simple. So you are a process, you send a request to the server with a message MR. The server receives your request. It computes the timestamp. It timestamp a reply message that will answer your request with its actual time, and then it sends to you this reply message that is empty. And when you receive the reply message, you set your clock to a value that is equal to the time that is in the reply message timestamp. And plus, what you have to do is that you have to correct your measure by taking into account what is the possible time that the message from the server spent traveling in the network. Because you know that if it spent the message, for example, 5 seconds, you know that the timestamp that the server sent to you has to be updated of 5 seconds because was measured 5 seconds ago. And how you estimate the things, since the only thing that you can measure as a process is the round trip time of the message, that is the delay between the time you sent to the request and the time you receive the reply. So what you do is that you imagine that the network is more or less symmetrical. This is the intuition. So you assume that the time that your message needed to reach the server is equal more or less to the time that the message takes from the server to reach you. And this means that the correction that you apply to the timestamp that you reach is equal to round trip time over 2. The problem with this algorithm are several. First of all, there is a problem on the accuracy of this correction. So there are a lot of cases in which taking round trip time over 2 just does not work, and we will see what is the problem now and what are the bounds on the accuracy of such thing. And the other problem are that the server can crash or can be compromised, but this can be solved with a redundancy approach. So you create multiple servers that are all synchronized, and you ask to each one of them, and then you take, for example, the average of these replies, or you try to filter bad server with some other algorithm. But we will not discuss anymore this problem. So what we have to discuss now is what is the bound on the accuracy that you reach, because assuming that the round trip time is totally symmetric is not a real assumption in a lot of networks. Assuming that there is a minimum delay of a channel that we call minimum, the error that you can do is bounded by a certain measure, and there are two possible worst case. The first worst case is the one in which the message that you send to the server is really fast. So M is the red case, MR is really fast and reach the server, and then the message from the server to you is really slow. In this case, the error that you make, if you look at the figure, is the difference that is between minimum and the middle of the segment, that is the segment that represents round trip time. And it's not hard to see that the length of this segment is actually equal to round trip time over 2 minus min. And since we are in the red case, it means that when you receive the timestamp and you correct it, you are correcting it in a wrong way, because the timestamp was actually measured minus that segment that we measured a unit ago with respect to the correction that you do. So in reality, you should apply a correction that is R round trip time over 2 plus round trip time over 2 minus min. But the correction that you apply is just round trip time over 2. And this means that there is an error, and this error that you do is that your clock is slower than expected and will be set of something that is minus r round trip time over 2 minus minimum delay with respect to the real clock. The second case is totally symmetric to the previous one, and is the one in which your message takes a lot of time to reach the server, and then the message from the server reach you in a really fast way. So it just take minimum time to reach you. And this case is the green one, and the error that you make is totally symmetric, but what you do in this case is that you set your clock to fast in the future, and will be faster than expected of round trip time over 2 minus min. And in both cases, we have that some problem on the accuracy, and the accuracy of Christian algorithm can variate, and its bound are plus or minus round trip time over 2 minus the minimum delay of the channel that you can expect. This is just a discussion on the things that we have been discussing before, that in this algorithm the server is a single point of failure, but you can solve it by using redundancy, and you can try to also solve some malicious failure using authentication. Now let's talk about the Berkeley algorithm. The Berkeley algorithm can be seen as the dual version of the Christian algorithm, in which in this time there is the server that asks to client the time and is the server that takes the step to synchronize. And the idea is that in this algorithm is that the server asks to each client a measure of time, then it takes all this measure, is try to compute an average clock of the entire system, and then he sends correction to each of the client in your system to try to synchronize them. And this is an internal synchronization algorithm. The algorithm works in this way. Periodically, the server sends a request of time to each client, and they timestamp locally when this request is sent. When a client receives a request of time to the server, it replies and it sends its timestamp. The master that received the reply computes the time in which it receives, so he computes the round trip time also in this case, and then he computes a difference between its clock and the actual clock of the client, and this difference is computing using this equation, that is the time you send the message plus the time you received the message, so divided by 2 minus the timestamp on the message from the client. And what the master does is to compute all this difference and then to compute the average of the difference, trying to exclude faulty processes. Faulty processes are processes for which the clock is too far in the future or too past in the time. And what it does then is to compute a correction for each process, and the correction is essentially given by the average that he computed, the average between the difference, minus the difference of the local process. And then he sent this correction to all processes. When a process, a slave process, a client receives this correction, the client apply the correction, and if it negatives, it has to slow down its clock. We will see how it slows down the clock in a few slides. This is an example. We have the master at the beginning, and he probe everyone for asking time, even itself, and then he measured the difference of the time read by the client with the time that is measuring. So in this case, he measured the difference between itself, that is of course 0. Then we have that client 1 is in the past of 10 minutes, so the difference will be 10 because the server is reading 3.5 and the client is reading 2 and 55 minutes. Then there is a difference of minus 5 minutes with the second client, and then the third client is considered faulty because the difference is more than 20 minutes. So the third client is going in the future with respect to the master with something that is above a certain threshold. And then the master computes the average of all these differences, and this average is minus 5. And note that when he computes the average, is filtering the bad computer, that is slave 3. When it's computed the average, he computes the correction that he has to send to everyone, and this correction is, it will be, okay, the average was 5, so minus 5, so the correction with the server that at an error of that the difference of 0 will be -5. The correction with the first process that had the difference of -10, so was 10 minutes in the past with respect to the other, will be +5. The correction for the process 2 will be 0, and the correction with process 3 will be -25. And then everyone try to apply the correction sent by the server. The accuracy of the algorithm depends on the maximum round trip time, and the server does not consider messages from processes that have a round trip time that is greater than some threshold. And of course, there are fault tolerance problem because a master server can crash. And in this case, we just elect a new master server. We will see the election in future lectures. And this algorithm is tolerating arbitrary behavior, some kind of arbitrary behavior, because if the slave sends a value that is too far in the future or is really in the past, what you do is just to filter that value when you compute the average of the value. So it's more or less failure tolerant to Byzantine clients. And now the problem is that this algorithm can slow down clocks of computer. And slowing down a clock is not possible. As we have seen in a previous lecture, is really a bad thing to do to jump backward in the past, and you can never do that. So what you do is that if you have to slow down your clock, you just start masking interrupt at hardware level. So let's say that you want to slow down your time of 1/2, then what you do is that every time you take just every time you receive two ticks from the hardware clock, you just advance of 1 your software clock. And so in this way, you are halving the number of ticks you receive from the hardware clock, and you are slowing down your time of 1/2. Sorry, you are slowing down your time of 2. And this is the way in which you slow down your clock. You cannot, remember, never jump in the past. And NTP is, for us, is just this, a hierarchy of server, where we have in the first level of the hierarchy, so the top level, the root one, are the servers that are most precise, and that are usually servers that have access directly to an UTC source. And we have other servers that are at lower level of the hierarchy and that are progressively more precise. And in this hierarchy, each one synchronized with the up server, so the servers that are more precise, using a variation of the Christian algorithm. And this is NTP for us. Then it uses a lot of other mechanisms to tolerate possible intrusion, to filter out bad measure, but we are not interested in this thing.